All right, so vibrational spectroscopy we established is kind of like what it sounds. It's all about molecules vibrating. And so an important concept in vibrational spectroscopy is the idea of a normal mode. A normal mode is a fundamental molecular vibration. And so I'll define what that means in a little bit, but there's basically, well, there are only two types of normal modes, only two types fundamental ways that a molecule can vibrate. Molecules can stretch and they can bend. And what does that mean? Bend means there's a change in the bond angle. Okay? One or more bond angles. There's a change. Stretch means there's a change in bond length. Okay? So fundamentally, everything comes down to only stretches and bends. You may have, there's a lot of different nomenclature out there. There's things like WAGs, there's things like scissoring. There's all sorts of names that are used in infrared spectroscopy literature and in vibrational spectroscopy literature. But those are just more complicated combinations of multiple stretches and bends happening at once. Fundamentally, all that can happen is a stretch and a bend. Okay? An overtone is something that can also happen, and that is twice the energy of the normal mode. So let's say you have some normal mode that's a fundamental stretch, like you have a linear molecule and it's just stretching like this. That's going to take some energy to do. Let's say it's 1,000 wave numbers. At approximately 2,000 wave numbers, you may or may not see, it depends upon whether or not it's allowed by symmetry, an overtone, which is just going to a higher energy vibrational state, but it has about twice the energy. Okay, and then you can also have combinations. Combinations are when you have, just exactly what it sounds like, two or more normal modes happening kind of together. They're mixed together. So maybe you have a bend and a stretch that are kind of both happening. So it's something like that. So the best way to think about this, the best analogy for this is a stringed instrument. All right, the normal modes are your fundamental notes. So let's say you're playing like A, okay? Let's say you're playing the note A. You're plucking one string. It's one string vibrating. Playing the note A has a certain sound, right? If you're to play an overtone, that would be holding the fret on a higher, to make the string shorter, right? But still playing an A. So it's the same sort of sound, but with a higher frequency, okay? And then a combination would be playing a chord, right? More than one. Usually, in vibrational spectroscopy, usually you're only going to get two things mixing, although in theory, higher things can mix. But yeah, it would be playing more than one note at the same time. And so sort of the normal modes are fundamentally all you can do with that instrument, right? It's like the strings on the instrument. And so there's certain notes that just don't exist. They're in between strings, right? Or in between what you can play, in between what you can play on the keys of the piano. And those are kind of analogous to certain types of bends or stretches that you just can't have in a molecule. They're forbidden by symmetry. And we'll see, go more into deep detail on this and see what sorts of bends and stretches are possible out of a molecule. And that depends highly upon what its symmetry is. One thing that we can calculate very quickly is the number of normal modes in a molecule. So the number of strings basically that we have in our instrument. And for a nonlinear molecule, this ends up being 3n-6. There is always going to be 3n-6 normal modes where n is the number of atoms. If you have a linear molecule, it's a little different. You're going to have one more normal mode. It's 3n-5 only. And again, is the number of atoms. So as an example, methane has 9 normal modes. Why? Well, it's not a linear molecule. So you use the 3n-5. And it has 5 atoms, 1 carbon, 4 hydrogen. So 3 times 5 minus 6 is 9. So it's going to have 9 normal modes. Water, also not linear. So you're going to use, you're going to use the 3n-6 formula. It's not linear. So 3 times 3 minus 6 equals 3. Oxygen is linear. And so for that, you're going to use the linear formula, 3n-5. Any diatomic has to be linear. There's no way to have a different orientation, right, with 2 points, 2 atoms. So it's 3n minus 5, so it's going to be 3 times 2, there's 2 atoms, minus 5, 6 minus 5, there's 1 normal mode. So normal modes have symmetry, kind of alluded to this. All normal modes have a symmetry. Broadly, you know, in sort of like spectroscopy tables that you might see, they're sometimes classified as symmetric and asymmetric. But we can use irreducible representations to more precisely define the symmetry. So what do I mean by that? I mean that any normal mode, here are the 3 normal modes of water, have some sort of symmetry associated with them that we can give a value. And it looks like my computer with Zoom and everything running is, you know, kind of laggy, so sorry about that, but hopefully you saw a little bit. Let's see. Oh, it's dead. Oh, there it goes. Some of them. It's just a lot of stuff for it to process. But there's, you know, this is a symmetric bend. It's A1. So strictly, what we mean by in a group theory standpoint, if we call something symmetric, strictly speaking, that's going to be something with A1 symmetry, something that has ones across the board in the character table. Everything else we'd classify as asymmetric. But that's not too important. More important is that we can give these different stretches and bends a symmetry. And so you can see this is given a B2 stretch. You can clearly see that's some sort of asymmetric stretch. It's going in and out, in and out. And this is a symmetric stretch. And we have 3 modes as we expect because of 3n minus 6 for a nonlinear molecule. Here, you know, normal modes of methane, there's 9 of them. You can see that there's a symmetric stretch. They're very symmetric. It's A1. These are called symmetric bends, but in a strict sense, we should call them asymmetric bends. But in symmetry, in spectroscopy tables, you'll often see them called as symmetric bends. But since it's not A1, we should call it asymmetric. But again, that distinction doesn't really matter. What matters to us, these are E bends, okay? This is an A1 bend. These are 2 E bends that have the same symmetry. They have the same symmetry and they have the same energy. They're degenerate, we say. We call them degenerate. They have the same energy. If you look at the character table, okay, for any E Mulliken symbol, an E Mulliken symbol has a dimensionality of 2. You know what that tells you is that there's 2 dimensions to this, so you're going to have 2 things always of the same energy. So in this case, the things are normal modes. And so that's why you have 2 symmetric bends of the same energy. Here you have 2 different T2 modes. 3 of them are stretches and 3 of them are bends. And these 3 bends are all going to be degenerate. They're all going to have the same energy because T2 is a Mulliken symbol that represents something that's triply degenerate. It has a dimensionality of 3. And same thing with these stretches. Even though they're T2 stretches, they're going to have different energy than bends, but they are all within one another degenerate. So these 3 here have the same energy. These 3 here have the same energy.